Welcome everybody to chapter 4, where we are going to try to find maximums and minimums. We're going to see how big things can be and how small they can be. Specifically, we're going to take a function. So let me draw us a function. Here's our x-axis, here is a function. What we're looking for is, this looks like a parabola, it may or may not be. We're looking for this output. This is the smallest output that we're going to get. That's the output that we're going to look for. We're also going to be looking for the input that gets us there, the desired input, because we want to figure out, how do you get the smallest output there? Now, as it turns out, we're going to define things for maximum and minimum, but I do want to just show you something. If I take this whole setup here and I make a copy of it, and I just move it over here and I take the very same graph and I say, let's do something we can't do on a board. Let's just flip it upside down. It apparently flipped just some of it upside down, but it'll do because it has a weird definition of it. Let's move this down to be down here. And we really have the same point. And so it's sort of the same question here. Now we have the biggest output. So we're trying to find the biggest and the smallest, and again, the desired input. But what I'm hoping to show from this is the idea that if you can find the smallest of something, it's sort of the same as finding the biggest of something else. Just flip the whole graph on its head. And so that's what we're going to be trying to do, is say that we don't really need to find the biggest, the smallest. Those are not separate things. If you can find the smallest of something, you can find the biggest of something. If you can find the biggest, you can find the smallest. Because if you know how to find the biggest and you actually want to find the smallest, flip things on their heads. So what we're going to do is we're going to define what we mean by biggest, what we mean by smallest, but then we're going to define them collectively. So let's start with minimum. We got a function, it's defined on some interval. That's basically just saying, what inputs are we allowing ourselves to have? And what does it mean to have the smallest, that desired input? Well, what it really means is that you have this output, f of c, and if you think that's the smallest output, that output must be smaller than all other outputs. Technically, not even all other outputs, smaller than or tied all other outputs. That f of x is the stand-in, it's for every single input x. So that's saying, hey, this is just all of the outputs. If you think you got the minimum, it's got to be smaller than all of them. That's what your intuition should say, that the minimum output is smaller than or tied with all outputs. And the maximum is almost the same thing. The only thing you do is you flip the inequality around to say, hey, it's got to be bigger than or tied with all outputs. Now, real quick, before we go on to this bottom piece, I want to point out that the minimum and maximum, the minimum is an output, and the maximum is an output. If I ask you, what is the highest point above sea level? What is the highest height above sea level? Your answer should be 29,000 feet or thereabouts. Your answer doesn't need to tell me where that occurs. The maximum height above sea level, 29,000 feet. It is so often useful to not just give this smallest output or this biggest output, but to give that desired input, the input that gets it. So we're going to talk also about where it is located. It's located at an input. And it's located at an input, because typically speaking, if you know the appropriate input that you're looking for, you can figure out what the output is, because that's what the function does. If I tell you that the maximum height above sea level, I don't tell you what it is. I don't tell you that it's about 29,000 feet, but I tell you where it's located, Mount Everest. Then you can now look that up and you can travel to Mount Everest and figure out what the highest point above sea level is. And figure out that it's 29,000 feet. So it's the distinction between where is it and what is it. Where is the input? What is the output? The maximum or minimum is the output. Its location is the input. Now, we're often going to talk about maximums and minimums sort of together. We want to group them together, even though they're kind of almost opposites of each other in a sense, not technically, but kind of. Intuitively, the maximums are like way up high and the minimums are way down low. But if you flip things on their head, then you're sort of looking at the same kind of thing. So we want a collective term for them. We're going to call these the extreme values, the extreme highest, the extreme lowest. We're also going to talk about these as absolute extrema and global extrema. These are synonymous. That means they mean the same thing. They're interchangeable words here. I will use them both. Uh, all that means is that's focused on the idea of who do you have to compare with to be the minimum or maximum. Absolute and global mean you're comparing with absolutely every single output. That there are no outputs that you're not comparing yourself with. The global extreme is the same thing. Global meaning everything, every single output. And we will have a counterpart to that coming up soon. I also want to just point out another quick definition that we're going to talk about endpoint extrema. Here's y equals root x. Where's the minimum? The minimum is down here at the left endpoint. It is the minimum output. The minimum output is located at the input 0. It is the output 0. And it's an endpoint extrema because it's just at the endpoints of the domain, basically. Okay, here's a question. I've drawn a couple of pictures. This picture here, we've got a minimum. Is there a maximum? And the answer is no, because it's going to go up forever. Same thing with these parabolas. If I back up, this one on the left has a minimum. It has no maximum because it keeps going up forever. So that means these maximums and minimums, they may not exist. How do we know that they exist? And so what I want to do is just take a slide here to try to understand how maximums, and I'm going to focus on maximums, how maximums might not exist. And method number 1 is this kind of thing. As x goes to infinity, y goes to infinity. And so if x goes to infinity, you might not have a maximum because if x goes to infinity, your output can also go to infinity. So there's no max. Now, is that a guarantee? No, of course not. That just because x goes to infinity doesn't mean that there won't be a maximum, but it at least gives us a chance. So if we're going to try to say we need there to be a maximum, we want to make sure the solution to this is don't let x go to plus or minus infinity. Okay, but that doesn't actually solve the problem because I can draw an asymptote and sort of have the same issue, that if this asymptote is at c, as x goes to c, y goes to infinity, and so there's no maximum, right? We're basically saying, how could we have a limit of infinity in some sense? And the issue here is that you can always get bigger by stepping close to c. The issue here is that the sort of biggest point, the end of this process in both cases, as you go towards x goes towards infinity, but you can't plug in infinity. As x goes towards c, but you can't plug in c, you don't get to that ending point. So x approaches the end point, but we can't plug it in. And so the solution is to make sure our definition, the domain, includes the endpoints. Don't allow yourself to get really close to C to approach C but not be able to plug in C, and then you can't do this. Well, okay, I'm going to come up with another way where it doesn't work. What if I do this? And say, what's the maximum here? Well, here's the thing. The maximum sort of wants to be here. It wants to be this output, the maximum there, But here's the problem. The desired input doesn't give that output. It gives this lower output. And that's a problem because if we go back to our definition, the maximum has to be an output that you actually get. We don't get this maximum. This is not an output of our function. It's on the output axis, but it's not a value you actually get out. And so here's what you can do. You can get this output really close to it. You can get this output really close to it. You can keep going. Basically, you can say, hey, as x approaches c from the left, if we call this c, y approaches L from underneath, from below, but we never get to L. And so any point that you claim is the maximum, if it's on this upward slope, I'm going to say, hey, just get a little bit closer to C. And you get a bigger output, and you can always do that. There's no maximum. The problem here is that there's just a weird jump. So the solution to this is don't let f jump. Make f be continuous. And it turns out if you put these three things in here, if you say f is continuous on a closed, which means it includes the endpoints, interval from A to B, this notation also means the endpoints, then f has both a maximum and a minimum on that interval. Guaranteed. There is a max. There is a min. This is a little bit like the intermediate value theorem in that it says, hey, this thing exists. There's going to be a maximum. You're not in one of those cases where you sort of go off to infinity or to an empty dot or something like that. There is going to be a maximum. Good luck. Find it on your own. This does not tell you where that maximum is. It's somewhere. That this actually works for height above sea level on the Earth, more or less. That the height above sea level is continuous. It's in. I mean, the Earth, you may have noticed, exists in 3 dimensions. It's actually a 2-dimensional manifold. So it's not quite single variable calculus, but the analog in higher dimensions of being a closed interval is satisfied by the Earth. If height is a continuous function, there is a maximum height above sea level. Even if you don't know where it is, even if you, like me, are hanging out here in New England and you have never been to Asia, let alone to Mount Everest, you know that there has to be a maximum somewhere. The same thing is true on the moon. Even before we had seen the far side of the moon, because fun fact, we only see one side of the moon from the Earth because it's locked as it rotates around us. We only see one side. Guaranteed there's a maximum height above sort of ground level for the moon and a minimum because of this theorem or the analog of it. There is a maximum, there is a minimum. We have no idea where it is. And I mean, until we actually put somebody and circulating around the moon and could take pictures of the other side, we have no idea where that maximum could be, but we know there is one. And here's the thing, once we know there is one, we have methods to find it. And so that's why this is actually one of the more, if not the most important theorems in all of mathematics. It's just sort of this minor little thing in its sort of full glory in a multivariable context. It is phenomenally important here. If you have a continuous function on a closed bounded interval, so no infinities, no missing endpoints, that's how you can get up to an output of infinity, then guaranteed you have a minimum and a maximum. It's such a huge deal, and it's also sort of just a minor point. That's it for this video. We're going to have another one where we actually start talking about how to find them and some nuances about this, but I want to leave with the extreme value theorem on the screen because it is such a huge idea, and it's one of those things where when we satisfy these conditions, when you have this checkbox, continuous on a closed interval, A to B, you want to notice it because guaranteed there's a maximum and a minimum. If you don't check both of these, there might be a maximum, there might be a minimum. We don't know yet though. and so it makes our lives much harder. I'll see you in the next video.